Hello everyone. In today's lesson, we'll talk about the applications of exponential functions, and I also want to go over the concept of natural log. Now, the reason why we want to go over this is because it helps us solve exponential equations and logarithmic equations, and therefore applications of them more easily and hopefully faster. Now, the term natural log has its roots in the number e. Number e is what we call the Euler number. Euler number is named after the great mathematician Leonhard Euler. And he is a European mathematician. He was born in Switzerland, as a matter of fact. He lived in 1700s, but spent most of his life in Russia, where he worked as a philosopher and professor, a mathematician and physicist. He even married a Russian woman and had 5 children, and her name, I think, was Catherine, a very pretty name. Okay, so back to Euler's number. The value of Euler's number, and here I'm going to impress you with my excellent memory. Not really. The value of it is 2.71828. And look at this now, 1828. So it's the 4 numbers that are repeating. So that's how you can easily remember this number up to 10 decimal places. And I don't remember the rest of the numbers. It's an irrational number, as a matter of fact. And I don't even try to remember it because there is no point to it. You can easily find it in your calculator, and I'll show you where and how. So Euler's number is indicated by letter E. Is usually hiding under the ln button, and that's what we're going to study today. That's natural log button. So you have to press second function and then that button in here. Okay, and I'm going to do that in my calculator. So second function, ln button, I saw E. I'm going to give you a power of 1 to see if I remember the number correctly. Yeah, it is 2.718281828 and 46 and some more numbers in there. Now try to locate it in your calculator. It shouldn't be that difficult too. And we're going to go over about the fact that Euler's number is very special, and that's why it made history in mathematics. Now, remember how when we graphed exponential functions, we said that they're all in the form y equals b to the power of x, and then we learned how to graph them, right? And started with 2 to the power of x, continued with changing the base to 3 to the power of x in order to study the changes in the steepness of the graph as we changed the base of it. Now, just like we drew the graphs y equals 2 to the power of x and 3 to the power of x, we can also draw the graph y equals e to the power of x. And here is an example of what this graph would look like, y equals e to the power of x. So just like any exponential function, it has the y-intercept right here at 1, and it's an increasing function. As we move left to right, it goes up in value. Now, I'm going to go back to decimals now. I want to show you something quite interesting. You probably went over it in calculus, but I always find it such an exciting concept, actually, to teach in functions as well. Why not? And we're going to perform a very simple exercise in here. We're going to draw the graph of y equals 2 to the power of x. So 2 to the power of x. And another thing I want to do is, so you see that the graph popped up is in red in here. And another thing I want to do is draw the graph of the derivative of it. Remember that the graph of the derivative of 2 to the power of x will give us the rate of change of this function at any point. So for example, the function y equals 2 to the power of x will have a value of 1 right here at x equals 0. The green graph is the derivative of it, so it looks like the rate of change at x equals 0 is a little bit less than 1, so it's between 0.5 and 1. I'm trying to move this, but it's not listening to me. So I'm going to perform the same drill, but now to the function y equals e to the power of x. And the derivative y equals e to the power of x. So basically we should have 2 graphs in here on the grid because we drew 2 of them. And this is what I'm going to do. I'm going to switch back and forth to e to the power of x, the red graph, and the derivative of it. I want you to keep your eyes on the graphs. So this would be e to the power of x. Red. This would be derivative of e to the power of x. Change again, back and forth. Did the graph move? The graph didn't move because, guess what? There was an overlap of e to the power of x and its derivative. So what does that tell us? It tells us that the graph of y equals e to the power of x and the graph of e to the power, the derivative of e to the power of x is the same thing. So in other words, it tells us that the rate of change of the function e to the power of x equals the value of the function at that point. So if that did make a lot of sense, and we don't have the time to go over, and that happens if you're not taking calculus, but I know most of you are. So if that didn't make a lot of sense here, I'm going to write the equation of it. So the value of the derivative of e to the power of x, or the rate of change of e to the power of x, equals the function e to the power of x. Okay, all right then. So that's what made number e special. Now, what is a natural logarithm? The natural logarithm is a very easy concept or thing to understand. So if we take the logarithm with base e of a number, then we'll say that the logarithm with base e, this part here, is nothing but the natural logarithm. And the reason why they chose the word natural, I guess, is because, you know, the function and the rate of change naturally coincided. So it's the same as if we wrote this. So in other words, the two circled ones mean the same thing. So we are going to practice only a couple of examples, very basic, very simple, there where we can see how we can use this concept. So the first one says ln x equals 1.532, and what we want to do is find x. So we don't see what the base in this log is, but we know because it's ln, the base must be e. So we're going to say that x must equal e to the power of 1.532. That would be the exact answer, by the way. Okay, so which means we can leave the answer in this form. But if we want to find actually the decimal value of it, then we can just go to the calculator, grab e here, bring it to the power of 1.5232. I don't remember exactly. 1532. No, I don't think it was this number. Sorry. I'm very sorry about that. 1.532. Okay. So 1.532. You know what? That's actually an opportunity for us to also see how the number, a small change in the third decimal, can 1.532 can alter the value of a number or can change the value of a number. Okay. So we got here the number 4. Where is it? 1a to the power, okay, equals 4.627. Sorry about that. So 4.627. So 4.627, 4.63, 2 decimal places would be sufficient enough. And now we'll continue with the next example. It's an example of an exponential function that involves Euler's number. So we solve it just like we would solve any exponential function equation, or exponential equation for short. But instead of specific base, natural base here, we have the number e. So we're going to factor, and the factors of it would be e to the x here. Two numbers that multiply to 6 and add to -5 must be two negative numbers, right? Okay, and we're going to make each factor equal to 0. e to the x must equal 2 or e to the x must equal 3. So now we're about to solve the equation. In order to solve for x, we're going to take the ln of both sides. And ln of e to the x will equal ln of 2. Apply the power law here. So x ln e equals ln 2. Now remember that when we say ln e, it's the log with base e of e that equals 1. So we're going to say x times 1 or x equals ln 2. And we're done with the answer. So that would be the exact answer, and we are supposed to leave it in this form. We do the same thing with the other equation, with the other factor. And we'll say that ln of e to the x equals ln of 3. So x ln e equals ln 3. Or even better, x equals ln of 3. And we're done. Okay? And now we are going